Probably shocked some of you with the formality of the geometry. And I promised you at the end that it's not as bad as it might have appeared on the last lecture, and that, in fact, the material that we talked about then are concepts that we're going to be using throughout the course, including today. Today, however, we're not going to do any formalisms at all. I'm just going to show you a bunch of really cool illusions that, but have a direct contact to what we talked about last time. So why don't we get started? What do you see here?
Some person with a really small torso and really big legs.
Looks like a baby on the top, a particularly grotesque baby. This is one where people wouldn't walk up and say, "Oh, what a cute baby." What do you think it really is?
Like some person lying down and then the baby just sort of lined up. It's kneeling behind her.
But so why don't you see it that way? You know what it is.
The continuation of the hip line to the side of the torso is really convincing at first glance.
All right, you get a gold star for that answer. That's exactly what it is. It's the continuation of this contour, and your brain has a built-in default. We'll talk more about this as we go along today. That a continuation like that can't happen by accident. I'll explain that in more detail in a second. All right, now one of the problems that we face, that a visual system faces, is that we don't have direct contact with the world. All you see are optical projections of the world on the back of the eye. Now, the problem here, at least it's construed classically, the world is three-dimensional, the eye is two-dimensional. So where the heck does your perception of 3D structure come from? You say, we have two eyes. Yeah, but that, I close one eye, world still looks 3D. So binocular vision is helpful to us, but it's not the end-all. And so one of the things we need to worry about is how we get around the projective ambiguity of the way light behaves relative to the eyeball. Now again, keep in mind the basic structure that we're dealing with here. What we're interested in as perceivers is I want to know about the structure of the world. So if I'm walking this way and I see I'm about to crash into you, I'll divert my path so that doesn't happen. So the structured light, the structured environment is what we're trying to learn about as perceiving, acting organisms. But we don't have direct access to the world. All we have is access, at least with respect to vision, all we have access to is patterns of light on the back of our retina. All right, so the big problem that people have been wrestling with for a very long period of time is how we go from the structure of the light on the back of the eye to some perception of the 3D environment. Where does that perception come from? Now, you can think about this from a variety of perspectives. You can say, okay, well, the brain is doing it. We've got physiological processes that are somehow determining what the 3D structure is. If you're, say, in computer vision, you say, well, we're going to write a bunch of computational algorithms to determine this. Or if you're a Bayesian statistician, you might say, well, we use our prior knowledge about the world to try and figure out what is out there based on the image data that we're given. But in all of these accounts, there's a lot of hand-waving going on. And what really is the case is somehow a miracle occurs. I don't know if you know that famous cartoon of a guy who, fills up a whole board with these complex equations, or two scientists talking to one another. And in the middle of these, there's a box that says a miracle occurs, and one scientist says to the other, maybe you ought to flesh this out a bit more. Well, that's the problem we face in perception. Most of how we do this, we don't know. We're going to spend the rest of the course talking about what we do know, but as we'll see, there are a lot of gaps there. So just to exemplify the problem a little bit more, let's say I have this ball-headed guy here, and he's looking out at all these curves. Notice they all project exactly the same thing on the retina. So optically speaking, there's, in terms of the stimulation on the retina, there's no difference between these four things. They're exactly the same in terms of the information that's available to the observer. And so the question is, how does the observer figure this out? Now, one obvious way is I'll just move a little bit, and yeah.
Why is, I guess I don't see why it's the same. Like, they have different shapes.
They have different shapes, but they don't produce different projections on the retina. I can probably demonstrate this for you. Can I borrow your notebook? Yeah. Okay, so let's take the edge of his notebook, all right, which is curved, right? You agree it's curved?
Yeah.
Well, let's see if I can make it straight. Now there's no curvature there because you're dealing with a projection. So curved things can project to straight things. The converse is not true. Straight things can't project to curved things, but curved things can project to straight things. That turns out that's going to be an important principle that we'll be talking throughout this lecture. But the net result in this particular case is all these project to the same point on the eye. Yeah?
Is it because if you were looking this way, you would only be seeing the vertical lines in each one of them?
Yeah, so let's take my arm right here, right, which is bent.
Yeah.
Close one eye. Now, do I have it just about lined up so you see it as straight?
Yeah.
Everybody else in the room can see it as bent, right? But there's one vantage point where it's going to project to a straight line. And as we'll see, this is a basis of a huge number of illusions because your brain makes the default assumption, when I see this as a straight line,
Right.
it's straight. You're not even going to entertain the possibility that it's curved, or even worse, right? Do my fingers look like they're connected? Get it lined up just right? All right? Everybody else can see they're not. But your brain says, hey, if they're connected optically, they're connected. I'm not going to consider another possibility. Notice, by the way, that this connection is a topological property. The curved or straight is a projective property. We're going to feed on the stuff we talked about last time.
Wait, I have a question.
Yeah.
So I guess the shape difference and how, like, looking at it from one point, it'll all look the same. But what about the length? So like this one here and that one there. Why wouldn't it be two different lines?
Because the length on your retina is determined by the angle that encases the object. So look at my hand here. Does it look big?
Yeah.
And then does it get smaller and smaller and smaller and smaller and smaller and smaller and smaller as they move away? So if you want to equate the retinal projection, things farther away have to be bigger.
Okay.
And guess what this slide is about?
Same thing.
Right? So this is one of the things that we have to deal with. So here we have an observer looking at this thing moving back and forth in depth, and this is what's happening on the retina, right? It expands, it contracts. This is a basic stimuli, by the way. So if you take a newborn chick, right, that's literally minutes old, and you do this, that chick will jump out of the way. That's a very basic stimulus that we respond to at an early age. So farther away things have a smaller optical projection than near things. And so that leads to the problem of how do we have size constancy? Why do I see you as the same size if you get up and walk toward me? Now, as we'll see later on, our size constancy isn't perfect, but we have some degree of Zive constancy. Now, the other thing we have to worry about is when objects change their orientation. So here we're looking at this rotating cylinder, and you see how the end cap changes shape in the projection. So it goes from being a straight line to a circle and everything in between. Do you have a question?
Yeah, it was about the previous slide. Is the size as it gets closer to you linear, or does it get a lot bigger? Like, it looks like as it gets closer, it's getting bigger faster.
Are you one of my engineering students?
Yeah.
Is that a linear equation?
No, that's why.
No, it's not. It's very nonlinear.
So
Even though it leads to what we call linear perspective. So in some respects it's linear, but let me hold off on that particular thing. Basically, it explodes as you get really close, and it sort of stabilizes as you get really far away. So here, this is also addressing your question, right? So when you see it on end, it's a straight line, and then as it rotates around, you see it as a circle or an ellipse or somewhere in between. But this is something we have to deal with too, because we see objects from different orientations and we see objects from different distances, right? The optical projection changes because of both of those factors, right? So if you look at me this way, in all my glory, and now I rotate like so, do I become a different Professor Todd? Your visual input has changed. You're seeing a completely different part of me. But we have the fancy word we have to describe that is what's called constancy, right? I may change my position, I may change my orientation. For the most part, you don't see me change in that way. You see me as the same Professor Todd. Now we can summarize those two things in this slide. So as you change the orientation of an object, its projected shape changes. This is often referred to as foreshortening or compression. And if we change the viewing distance, the projected size changes. This is often referred to as scaling. They're largely independent of one another, not completely so, but they're largely independent. So the foreshortening is pretty much solely dependent on, I guess that's a contradiction in terms, is the foreshortening is mostly affected by orientation and scaling is mostly affected by distance. And here's an example. We have the two objects. So the difference between this and that is foreshortening. Difference between the length of the object here and the length of the object there is scaling. Questions about this before I go on, all right? So the only point I'm trying to raise here is that the optical projections are changing for a whole lot of reasons. But we don't want our perceptions to change, right? You want to see the same person regardless of what pose I'm striking and what orientation you're looking at me for. It would really look weird, right? If somebody giving a lecture and I just change from one persona to another every few seconds. That's not what you want. The visual system wants stability. And remember when we talked about the Klein model of geometry, that's what it was all about. So what Klein was looking at are what properties are most stable under change. And as we'll see as we go through the course, those are the ones that the visual system really focuses on. So if I get some properties like the length of my arm that's changing like crazy, maybe that's not a good thing to focus on. Maybe a better thing to focus on is that it's one continuous thing. And that's, as we'll see, there's a whole hierarchy of properties that the ones that are most stable are the ones that we're most sensitive to. All right, in order to resolve projective ambiguities, human observers are biased to interpret to perceive the interpretation that is statistically most likely in the natural environment. Now this is, there are a lot of regularities in the natural environment that you can sort of build into the system through evolution or through learning. Some of them are really, really general. So for example, unless there is information to the contrary, objects will be perceived as resting on the ground. So let's pick on you this time. You have a choice in interpreting this scene. I can be 6'2" Professor Todd, standing about 7 feet away from you, or I could be 6'2" Professor Todd, hovering in midair about this distance away from you, both of which would produce exactly the same optical projection. Which one's more likely?
I would say 6'2" tall.
The one that's resting on the ground. And that, in fact, is a really basic constraint. If an object looks like it might be resting on the ground, you're going to interpret it that way unless there's specific information that's telling you otherwise. Here's another one. There's a strong bias to interpret scenes such that depth increases with height in the visual field. Let's pick on you this time. Come on up in the front of the class. All right, I want you to stand in front of this row.
Okay.
And in your visual field, who in this row is highest in your visual field?
Her back there.
Her. And who's the next highest?
The guy in the red.
And who's the next highest?
The pink, orange color.
Who's the next highest?
The white shirt.
Well, actually, she may be a little higher because her hair sticks
her
up.
hair
But
does go higher.
and who's the lowest in your visual field?
Her.
Okay, good. Why is that the case?
Because they're farther in the back, so it looks like it's going up.
Right. We're looking on the ground plane, right? If we were on the ceiling, it wouldn't go that way. You can go back to your seat now. Thank you. Right? So the basis of this constraint is that we see the environment, all the objects that we see are almost always resting on the ground plane. And the ground plane has that property. So if we were bats, for example, and we hung off the roots of caves, then maybe the opposite would be true, right? So if everything was attached to the ceiling, then you get the opposite relationship. The height in the visual field, things would get higher as you go lower. Here's another one. Convex interpretations are perceived over concave ones. Now this one might strike you as completely arbitrary, but we'll see a number of illusions that are based on it. It turns out if you look at natural statistics, now I know our ancestors lived in caves, but they spent most of their time outside of caves, right? So if you look at a globally convex object, there's much more regions that are convex than there are regions that are concave. It's just a statistical fact about the environment. And our brains have attuned themselves to that. So this is a pretty strong bias. And then finally, we'll spend a lot of time on this one. Interpretation involving generic views are preferred over those that require a specific vantage point. So let me unpack that one for you a little bit. So there's the example I gave before, right, where I was holding up my fingers like so to try and get it so in her visual field, the fingers look like they're attached. Everybody else in the room can see that they're not. But there's one vantage point where they look the same. That's called an accidental view, right? If I have my fingers like this and you just picked a view from random, the odds are vanishingly small that you would pick one where they project such that they terminate together in the projection. And that's what's called, so the things that have a vanishingly small probability of occurrence, if you were just picking views at random, those are called accidental views. Now, often they're not accidents because sneaky psychologists are trying specifically to fool you, right? But so if I bend my arm so it looks straight to you, I can use that as a basis for an illusion because your brain is going to assume it's straight. If I do this, so my fingers look like they're attached, your brain's going to assume that they're attached, but everybody else who's having a generic view can see that they're attached. So a generic view, think about it this way. You pick a view at random, would my fingers look attached? So for everybody in the room, except you, you can see clearly that they're not attached. That's an accidental view. What everybody else sees is what's called a generic view. All right, so let's consider how this works in action. Let me pick on you this time. I haven't picked on you in a while. Tell me what you see. Up there.
Okay. I see two cylinders. The one on the left looks taller than the one on the right.
2 cylinders, the one on the left looks taller than the one on the right. How confident are you in that?
Not confident, but that's
Oh,
what
only
I
because
see.
you're in this class.
That's what I see.
How many of you see the same thing she did? All right, so you should have confidence in your perceptions, right? They're shared like everybody else. But you know enough to know that I wouldn't ask you something like that unless I was about to fool you. So this is what it really is. Whoops.
I was like, wait, what?
That's not what it really was. Oh, give me a break. All right. It worked on my computer. I wonder if they took Flash off of here. In any event, what you should have seen, had my Flash demo been working, is this is actually farther away. So there's a post that you can't see behind it that sticks out like so. All right, so this guy is, this guy is farther away than that guy. And so what the post is, this is much closer than this one, which is what's causing the projected size to be bigger. But because you can't see the post that's holding it up in the air, you interpret it to be the real size. Now, what the demo should have shown is this thing would rotate around. You'd see the post supporting it. It would go back to this position. You know exactly what's going on, and this still looks bigger. All right, so your knowledge doesn't help. This is really basic. Again, I apologize for this demo not working, but I guess Flash is going away forever, so it's good I'm retiring. All right. Now, if we have information that things are rising off the ground, that's a different story. So here we have an object sitting on the ground. Notice the indirect reflections here of the blue shining on the ground and the shadow here. So if we do this slide, right, notice the indirect light isn't attached to this edge anymore. The shadow isn't attached to that edge. And that provides information that's telling you this is hovering in the air. So you can override the default assumption that things are on the ground as long as you give the subject information to show that's the case. Oh, I hope this one doesn't not work. Okay, let's pick on you. Tell me what you see here.
It's like a concave. I don't know.
All right, so this region under the arrow is concave,
Yeah.
like that?
No, like going down. I don't know how to describe that, but
How do you see this? Is this concave or convex?
concave.
Concave. Do you all see it as concave? It's actually completely ambiguous. Let's see if this works. I don't know why the other didn't work. Now does it look concave or convex? And now let's flip it again. And we'll flip it again. Can somebody explain which bias is responsible for this? Notice whichever way you see it, you see how the surface is slanted backward like so? In this, right? Does it look like it's slanted backward this way a little bit? And when I rotate it, it still looks slanted backwards like this. All right? This is a completely ambiguous stimulus. It could be this, it could be that. Both of them are statistically, well, I take it back. If we didn't account for ecological constraints, they'd both be equally likely. But our brains are biased to see ground planes over ceiling planes. And that's what causes this illusion. Here's another example. Let's get you this time. What do you see?
Looks like a ripple.
In this area right here, is that a bump?
Oh yeah, it's a bump, and then it's like goes in, and then like a circle, like a bridge outside, and it's all bumpy.
What if I told you it was really a dimple?
I would not believe.
Well, let's see if I can make you believe. Is it a dimple?
Yeah.
And now it's a bump. Again, the key principle here is that in both of those interpretations, you're seeing the surface slanted like so and not like so. So that's the bias. This is preferred over that. Pretty powerful effect. Now, this can cause complications in the next slide. Now let's pick on you again. What do you see here?
A larger bump in the middle.
A larger bump in the middle. Everybody see a larger bump in the middle? All right, now this one has a property that I want to highlight here, is one that's going to come up often. You see these T-junctions here where these lines end and are terminated by this one right here? Remember we talked about that before in the last sections? When you get a terminator of a line, what causes that? Think Grossberg and Mangola model, right? So when my arm terminates, when I put it behind my body, what's causing that? My body is occluding the arm. And the occluding thing is always in front of the occluded thing. So that's a very powerful source of information that can override these built-in biases. So let's look at how this guy behaves. Now what do you see? Does it look like a big tongue that's hanging down? Can anybody see it reverse so it's actually a bump that's pointing downward? You can see that? Anybody else? How many of you see the tongue? How many of you see it, the bump pointing downward? So tongue is the majority. Now the interesting thing here is what's causing that is that these regions won't reverse because of these T-junctions, this area is in front of that area. And you're biased to see this over that won't override that information from the T-junctions. Here's one last one I'll show you related to that. Let's pick on you this time. What do you see? See a small bump? All right, now this time I'm going to turn it over and you'll probably still be able to see the bump. I want you to keep looking at it though. I want you all to look at the bump and raise your hand if it's still a bump. All right, now look away from it. Look back. Is it a dimple now?
Yeah.
Now again, all of these are examples where you have a bias to see ground plane over ceiling plane. That's this built-in bias that we have. Now there are wrinkles on it. You can push it around by having other sources of information, but that's the main point I want to make in these particular slides. Let's move on to another one. Let's pick on you. Tell me what you see.
4 dots.
Or do they look 3D?
No.
They don't look 3D?
They don't know.
Raise your hand if it looks 3D. Okay, what do you describe it?
Describe which one?
Do they all look like bumps?
They look like, I don't know, they look like eggs.
Eggs, convex things.
Yeah.
All right, these two are actually concave. The way you can tell that, notice the shadow is inside the object. That's a surefire information that it's a concave object. But we have a really strong bias to see convex things over concave things. All right, we'll get now to my example with the fingers. What do you see here? This is an actual sculpture in Black Hawk, Colorado. What do you see? Pick on you. You're the appropriate one here.
Like, just like a bunch of, like.
This one.
Random, yeah, just a bunch of like random squiggly arches.
All right, so this is not connected to that, and this is not connected to that. What do you see here? They're the same object, right? It's just in one case, you're looking at it from just the right vantage point that makes these contours come together. And you can't see this to be that, even if you wanted to.
Is that the same thing that applies to, you know, those like chalk drawings where it looks like you're like walking down into the.
Well, I'll talk more about that later. That's a little, yeah, basically, it's the same thing. All these illusions are related to one another. There are different wrinkles on them, but the chalk guy is named Julian Beaver. In fact, I'll show you a film about him at the end of class. All right, so these are non-accidental properties. What makes non-accidental properties important is that they don't change as a function of orientation, as a function of viewing angle. So let's say I have a straight line. Let me borrow your pen. All right, does it look like a straight line? Everybody? Still look like a straight line? Still look like a straight line? Still look like a straight line, right? I can view this from any vantage point and it'll project to a straight line. That's what's called a non-accidental property, right? Now you could have a not straight line, like the crook of my elbow, that you see from an accidental view that looks straight, but your brain says, no, I'm not going to entertain that. If I see a straight line, I'm going to assume it's straight in the world. Straight line is what kind of property? It's a projective property. It's preserved over projective transformations, which means that's what makes it reliable, because you know, when I move around a different vantage point, the sizes of things change, the shapes of things change, but straight lines don't change. They stay straight. Cotermination, that's what we just saw in this example here. Cotermination is another accidental property. So if things coterminate in the image, you're going to interpret this as that, and you would never even consider that, right? So if things line up in your image, you're not going to consider the possibility that that alignment occurred by accident. And the reason why that is that cotermination is also preserved under arbitrary viewing directions, right? So my elbow is attached to my shoulder. It doesn't matter what I do. I can walk around the world, I can bend, I can flex. My elbow's always going to be attached to my shoulder. And so the fact that they attach in your retina, your brain is going to assume they're attached in the real world. This is a topological property. And then finally, we have parallelism. This one's a little less general, but the idea is if you see parallel lines in the image, you're going to assume that they're parallel in the world. Another example of non-accidental property. Yeah?
So is the example from the slide before not accidental viewing?
Which one? This one?
Yeah.
This is an accidental view. This is a generic view. So from almost any vantage point, you'll see this. If you go to this sculpture, there'll be a specific point where it says, put your head on this spot. And that's where you'll see it just right. Who asked me about Julian Beaver? Julian Beaver stuff works the same way. You have to look at it from one specific viewpoint to get the effects that he's creating. And when that's the case, that's called an accidental view. Though not in Julian Beaver's case, I suppose that's misleading because that's the one he wants you to look at it from. And again, just to point out, parallelism is an affine property. Straight versus curved is a projective property. Cotermination is a topological properties. So these are the properties that the visual system relies on most heavily. And we can make sense of that because of Klein's theory, right? Where you can show formally that these are the most stable properties. These are the things that don't change when we're moving about the world and getting these crazy changes in our projections. That's why they're so reliable as sources of information. How many of you have ever been to the Exploratorium in San Francisco? Anybody? All right, let me show you a wonderful example. Before I start this movie, I should point out the guy who's narrating this is named Philip Zimbardo. Any of you see the movie on the prison experiment? Well, Zimbardo is the infamous character that did this. He's regarded as like one of the best intro teachers in the country. He's at Stanford University. And this movie is from his lecture. Though most of what he says in here is total bullshit. But I'll explain that a little bit later.
Lights, camera, perception. When you were little and some big kids pushed you around, did you ever fantasize about becoming bigger all of a sudden? Well, I did, and now I can, at the Exploratorium, San Francisco's Science Museum. How did I do it? The easy way, by manipulating your perception. When you first saw me, I appeared to be normal size, but you couldn't see the rest of the room. But as the lights came up and the camera pulled back, your brain performed a new instantaneous analysis. It now saw me as small. It added up all the visual information it had about my size and the size and shape of the room. And then it added in everything it knew from experience about the usual shape of rooms, that they're rectangular and have right angles. So when I walked over here, your brain was convinced I was growing incredibly large because there was no other perceptual explanation, even though it wasn't logical. Let's look at it again, only this time from a different perspective. The room is not rectangular at all. It's totally distorted. There are no right angles anywhere. So that makes this clock, which is large and oval, look the same as that clock, which is small and circular, from your other perspective. The floor slopes upward. As you can see, the ceiling slopes downward. So I'm not getting larger at all. You're just misperceiving my size because you think that you're the same distance from me when I'm over here as you are from me when I'm over there. But in fact, I'm twice as far away.
Has anybody seen that illusion before? They actually had one at COSI for a while, but it was a temporary exhibit. Here's another example of it, of two twin sisters. All right, now why did I say that what he said about it was nonsense? There's a simple explanation to this, and that is the fact that these lines are parallel and these lines are parallel like so, right? It doesn't depend on you knowing the normal shape of rooms. It involves this basic non-accidental property of parallelism. So your brain sees these things as parallel in the image, and it says, by golly, they're going to be parallel in the world too. And that's what's driving the illusion. It doesn't depend on you knowing the size of people or the size of clocks or any of that. It's just the parallel lines. So here's how you set it up. The room is actually a trapezoidal shape, as Zimbardo described. There's a specific vantage point, a pinhole here, where if you look at it through that pinhole, everything will line up just right. This illusion is due to a guy named Ames, who was a psychologist from the 1950s, and he constructed all kinds of crazy things. He had one that is called an Ames chair, where it's a bunch of completely unattached sticks that are hung from the ceiling in just the right way, that if you look at it from just the right vantage point, they all connect sticks and it looks like a chair hanging in midair. Again, in that case, it's not parallelism that's driving it, it's the cotermination in the optical projection. And here's what it looks like if you look at it through the peephole. All right, let's pick on you in the back. Tell me what you see.
Triangle?
Does it look anything strange about it?
It's three-dimensional.
What do you see?
It seems like it's an infinite object, if that makes sense. Like,
No, it makes absolute sense.
way for it.
Right, so let's think of it this way, right? You have this surface is in front of that one,
Yeah.
and you have this surface is in front of that one, and this surface is in front of that one. Those three combinations of things just can't happen. That violates what's called transitivity. This is what's sometimes referred to as an impossible figure. Anybody have an idea of how it was made?
Manipulating the shades.
What's that?
Manipulating the shadows.
No, they're not playing games with shadows here, and I don't think the shadow is necessarily revealing anything. Yeah.
I think one of the corners doesn't actually connect, and it's just a termination perspective, accidental perspective.
You can do it that way. I'll show you another example where that's how it's done. I think this one is this piece right here is not part, so this connection isn't real. It's just a flap that sticks up from this object, and if you align it just right with that edge, your brain interprets it as if they're connected to one another. I'm not completely certain on this image how they made it. There are a number of ways you can do this. Here's another example that is what you described. So you see the impossible triangle, but notice the shadows. So here the shadows are really giving it away. And if you move the object, like so, right, you see what's really going on. But then if you put it together just right, then your brain says, oops. Then your brain says, hey, this alignment cannot happen by accident. And so what your brain is doing here, basically, it's saying, I'm going to see this as an object that is physically impossible to produce over what's really there, because I insist that this be part of the same contour. Very stubborn brains we have. Here is another version done a little bit differently. This guy is a Belgian sculptor. So this is what it looks like from the accidental view. Another impossible triangle. This is what it is in reality. And what your brain is saying when it sees these straight lines, I'm not going to entertain the possibility they might be curved. So you couldn't see this if you wanted to. So this is somewhere in Belgium. I've been to Belgium many times. I think it's in eastern Belgium, some town there. A student looked it up one year, I showed this. But I do like Matthew Haymaker's. Here's another example of his. All right, this is an impossible cube. Whoops. All right, you see the impossible cube? Makes no sense. But now let's see him show it in motion. So even now that you know what it is, you can't see it that way. Because you can't, right? You have all these straight lines in the image, and your brain is saying, I will not entertain the possibility that they might be curved. That's just not allowed. Now this gets us to these images. I've been doing this lecture for a while. This is actually one of my favorite lectures, and I get all kinds of emails from students after the fact who send me examples like this, where they exploit non-accidental properties, where you get these ridiculous figures. So here's one where some bald guy's holding a picture of Queen Elizabeth that's aligned just right, so it looks like it's all one head. This is a popular technique where you take a magazine cover of somebody and stick it over your face, and if you get it just aligned. One of my favorites here. What's going on here? Looks like a guy with a really long arm. It's actually two guys holding their arms out. Now, sometimes these are accidental, sometimes they're planned. This one a student sent me a couple of years ago, and he put in the message, he said, this slide struck me as the essence of your course. And I sort of agreed with him. So he's just holding up a picture of Salvador Dali in front of himself to get this is obviously accidental. What's going on here? Right, the woman fell asleep and her dog sitting next to her, and somebody saw it and took the picture. There are probably 10 million photographs like this one, and probably another million like that. These next two were also sent to me by students. When my nephew was little, he's really into optical illusions, and when he was visiting, I would let him go through my PowerPoint slides. And he spent about 2 hours on this lecture, and he came up to me afterwards, and he's like 14, he said, "That's got to be the best lecture in the history of the world." Here's some more. You imagine posting that on Facebook and not noticing the, so what's going on here?
The arm makes it look like there's a naked lady standing behind her.
Right, so the woman in the front, this is her arm, but it's aligned with the torso of the woman in the back, so it makes her look absolutely naked. Now, I could easily imagine putting that in Facebook and not knowing what you just did. Or similarly, this one, what's going on here? Pay careful attention there. All right, can you imagine putting that on Facebook? Now, this is not what it appears to be. This is the crook of her elbow that is aligned just right. And then there's this strange one where her purse is situated just right. The net is filled with thousands of these things, so they're not hard to find at all. But they're all examples of these accidental alignments. Yeah.
So, in the room perspective example, you said that the guy was kind of making it up when he said that it depended on your previous understandings of what a room looks like, and kind of like top-down processing. But like, aren't these examples of you like you have the expectation that that's what it is, so that's kind of also partially why you see it?
I don't think so. So, which is more likely to see in a picture, the crook of a woman's elbow or the crease of her butt? I'd say the elbow is much more likely. It's the alignments that matter. I'm not saying there are no top-down effects on perception. They usually involve what it is that you're attending to, not how you interpret the information. Now, I should tell you from the outset that my theoretical persuasion is such that most things are bottom-up. So if you ask me to interpret almost anything, I'll give you an explanation like that. There are other people who argue, no, everything is top-down. They tend to not be the people that actually study perception, though. All right, so Zimbardo is a social psychologist. He's not a perceptual psychologist, and he certainly doesn't know the literature on this stuff. It's surprisingly how little our knowledge helps us. And you can get that from a lot of the illusions I've shown you, is once I show you what happened, you still see it the same way. It doesn't matter that you know what's really there. You can't override that default assumption that the brain is making. All right, that leads us to the last part of this. We're going to talk about anamorphic art. And what anamorphic art is, it's art that looks distorted. So let's say you paint a painting like this, and you have a cylindrical mirror here, and if you look at the mirror, it looks like there's a thumb in it. Because from just the right vantage point, right, everything projects. This is painted in such a way that if you look at it in this particular mirror from just the right vantage point, it'll look like a thumb. Now, this kind of art goes way back. The first example I know was by Leonardo da Vinci. But it's pretty popular now. And the most popular guy, here's another example. Again, using that mirror technique. And that gets us to Julian Beaver that one of you asked me about earlier. So what do you see here?
Looks like a guy crouching down, holding up some letters and saying, "World and a very tiny woman on top."
All right, so let's get to your question before. What's your top-down knowledge telling you?
Tell me that's impossible.
There are no really tiny women
Unless it's
outside of the movies. Just doesn't happen. All right, but so what is telling you that that's a really tiny woman? What he's doing in a lot of these illusions, he's faking it out and making you think that she's closer than she really is. And he does that by altering the perspective on these letters so it looks like they're all at the same depth, when in fact they're not. So here's a movie that talks about Julian.
Depending on how you look at it, the work of art can have plenty of curved appeal. Harry Srinivasan shows us the work of a master.
Millions of art lovers have traveled the world to see marvelous Monets, gorgeous Gauguins, and remarkable Rembrandts. But all those art lovers would fit into a tiny corner of this museum, the virtual museum of the internet, where untold numbers are at this very moment seeing and marveling and sharing the three-dimensional pavement drawings of English artist Julian Beaver.
So really the internet becomes your pavement.
Exactly. That's my medium, really. If it wasn't for the internet, my stuff would be totally unknown.
This is Julian being rescued by Batman and Robin from the ledge of an imaginary burning building. The sailboat in this picture isn't real. Neither is the pool it floats on. The reel of hose is not real. Neither is the water, nor is the drain. And Felix the cat isn't really climbing out of a manhole wearing a costume for Chinese New Year. We caught up with Julian Beaver a few days ago in New Orleans as he began his latest creation.
In the past, I used to get quite insecure really on the first day, not knowing that I would have enough time to get it finished. But now I try to be a bit more cool about it. I know I've done so many of these and they always do get finished.
He was commissioned by a business group to come up with a theme that reflects New Orleans city life. First, he draws his design in miniature.
It's a very expansive drawing, this one. It's figures and things coming out of a hole, exploding into life, blowing a fanfare outwards to the world.
Before chalk touches concrete, comes a road trip that helps his sketch grow in scale. The entire process will take 3.5 days. Beaver says the first day is the hardest.
Looks like it's just a bit of scribble, but actually the information there is probably the toughest bit to get done.
And there's the physical toll, from drawing on the ground and running back and forth to look through the camera hundreds of times just to gain perspective.
Feeling pretty tired now. Well, none of us getting any younger. Oh, we're right.
To get the full picture, you have to see Beaver's work through a lens.
I think because the camera limits what your brain can do. It limits the brain's ability to judge distance. It makes you only use one eye. And therefore you can make the brain believe stuff that otherwise it wouldn't do.
So it's really, your art wouldn't be your art without the camera.
No, you need to have a lens or a camera or something to view it.
The original plan was to draw on a busy downtown sidewalk. The threat of rain moved him to this covered valet entrance at Harrah's Casino. How much of a following does Julian Beaver have? Just ask a parking valet.
Yeah, I've seen a lot of his paintings on the internet. It's amazing, you know, it's how it comes to life.
After art school, Beaver became a busker. He supported himself by making two-dimensional drawings on pavement for pennies from passers-by. He turned to three-dimensional art not by error, but by trial, starting with a woman in a swimming pool. Her leg didn't come out quite right.
I didn't really have the experience at that time to realise exactly how to do that leg in relation to the height of the camera.
But he learned from that mistake and has been wowing people ever since.
It looks dimensional to me.
It does look dimensional.
Yes. Isn't that amazing? This picture.
So typical New Orleans.
And she hasn't seen anything yet. Beaver's bare bones chalk outlines are fleshing out.
So we're seeing who? Is Louis Armstrong bursting through the sidewalk?
Well, it's Louis Armstrong if I can get a likeness. If I can't, then it's just any musician.
And when it all works, it looks like this. His New Orleans drawing fully realized. An amazing piece of art. But like all of Julian Beaver's pavement drawings, it is destined to be swept away, erased by time.
It doesn't worry me at all the fact that the drawing will disappear after a couple of days in the rain, because the final product is the photograph, and if that photograph goes on the internet, then thousands of people will see it, and it'll be there forever. So it doesn't vanish really. The drawing on the ground is just a vehicle.
Just one more way Julian Beaver keeps things in perspective.
So here's an example of what's going on here. You have, looks like a tiny person sitting on top of the globe. This is what it really is. Now, Beaver is not alone in doing this kind of stuff, exploiting non-accidental properties. As I said, this Anamorphic Art has become more popular recently. I'll show you a couple more examples. Here's one in, this is someplace in Europe, I don't know where it is, but you see a sort of ethereal square with a circle in it. Here's what it actually is. But if you look at it from just the right vantage point, you see that. And here's my favorite of all. What do you see?
It's the Medusa.
Medusa, very good. With the snake's heads cut off. This is what it really is. But it all comes together when you put it right together. I found another video I have to show you. How many of you know the group OK Go?
Yeah.
So let's do one more video and then I'll pass back the exams. This is sort of accidental properties on steroids for this one. I have no idea how long it would have taken to set that up. Okay, that's what I have for today. I'm going to turn back the exams now. Let me just say from the start, you guys did spectacularly. This is, I've given this same exam